Good afternoon, everybody. This is Joe Veasey with aeSolutions. Welcome to our webinar on choosing a risk assessment methodology. This webinar is the first webinar in a series of 3 webinars. The second webinar, which will be announced for presentation in January, is the capabilities of quantitative risk assessment and its applications. And the third webinar will be presented in February, and it is the best practices for ensuring that your risk assessment is trustworthy. So I want to go over a brief agenda of what we're going to be doing today. The first thing is I'm just going to take a brief look at the safety life cycle, the IEC 61511 safety life cycle. And then we're going to spend a little bit of time going over process hazard analysis, what the purposes and the various types of process hazard analysis. From there, I'll introduce the purpose of risk assessment. And then finally, and for the bulk of this webinar, we'll be going over the several of the various risk assessment methodologies and some of the trade-offs. So let's get going. So this is the IEC 61511 safety life cycle. It is primarily used guiding a organization through the requirements of designing and implementing safety instrument systems. However, the purpose for me showing it here is that you can see at the very top, the very first thing you're doing is you have to do a hazard and a risk assessment. And while the standard kind of speaks to this as one item, it's actually 2 separate things. The first is a hazard assessment or process hazard assessment, PHA. And then after that is the risk assessment aspect of it. So let's go over what is a PHA and why do we do it. So the actual purpose of a process hazard analysis, or PHA, is to define your credible hazard scenarios. And there's different methodologies you can bring to bear to do that. But whichever methodology you use, when you walk out of a PHA, you have 5 things in your hands. You've identified those credible hazard scenarios. You've identified the causes, the credible causes to those scenarios. You've identified the consequences, and you have ranked the severity of those consequences. You've identified any safeguards that help you prevent the hazard scenario from propagating into the full consequence. And then also you've identified several PHA recommendations. So again, the purpose of the PHA is to identify hazard scenarios, and it really answers the question, is there a problem? There are different PHA methodologies. The one that's most commonly used in the process industry is the hazard and operability analysis, or HAZOP. It is really seen as kind of the sweet spot between the amount of energy that you put into a PHA and the quality of information you get out. Other methodologies listed in the OSHA PSM are the checklist, the what if list, the what if checklist, the failure modes and effects analysis, and fault tree analysis. So the next thing we're going to talk about is the risk assessment, and basically what it is and what its purpose is. Some folks, when they think of risk assessment, they are talking about what I would call consequence analysis, and there are yet other variations of it. But for the purposes of the standard IEC 61511, or ANSI ISA now, the latest one is ANSI ISA 61511. It's really a means to ensure that the frequency and the severity of a consequence falls within an organization's tolerance for risk. And usually the way that an organization will couch its tolerance for risk is in a risk matrix. So here is a risk matrix, and you can see over on the left vertical axis, there's a consequence severity, and on the bottom horizontal axis is a consequence frequency. And where they intersect is an indication of whether or not a given amount of risk is acceptable. I guess I should have said that, risk is really a function of consequence severity and consequence frequency. So it is usually by this means, a risk matrix, that an organization will couch their tolerance for risk, what their risk tolerance criteria is. So again, a risk assessment really determines whether a hazard scenario is the way it currently is going to happen with your current set of protections, whether that hazard scenario is compliant with the corporate risk tolerance criteria. And it answers the question, how big is a problem? Looking back, a PHA really asks the question, or answers the question, is there a problem? And if there is, the risk assessment is what is often used to determine how bad the problem really is. A risk assessment will also identify if any and how much additional risk reduction is going to be required for a given scenario to meet the corporate risk tolerance criteria. Now, not every scenario that you will produce in a PHA would be suitable for use in a risk assessment. Usually, you will only select a proper subset of those PHA scenarios to be taken to a risk assessment based on some criteria. The most common criteria would be the consequence severity. So an organization might decide only to take scenarios that would result in a major injury or a fatality, for instance, to a risk assessment, and anything that's in the minor injury category, they would not put the additional diligence into controlling risk for those low consequence severity scenarios. And then another criteria oftentimes is just basically the study team's opinion as to whether or not a scenario should be taken to a risk assessment from the PHA. When you do a risk assessment, you can do it either in the same venue as the PHA, or you can do it after the PHA in a separate venue. And there are trade-offs with both. If you decide to execute the PHA in the same venue as the PHA, if you decide to execute the risk assessment in the same venue as the PHA, the advantage is that you've already got the team's mind wrapped around that scenario. You don't have to reintroduce a scenario. However, because the skill sets you need in the meeting to be successful at a PHA is not the same skill sets that you need to be successful at a risk assessment, sometimes it's advantageous to do the risk assessment in a separate venue. There are synonyms for risk assessment. Some of them are SIL allocation, SIL assessment, SIL assignment, etc. Basically, a lot of times people will look at the activity of deciding what the safety integrity level that is needed for a hazard scenario is. They'll do that within a risk assessment, and they will accordingly give the risk assessment activity the name, SIL classification or SIL determination, etc. This webinar is not about safety instrumented systems, but there's a couple good points that we can make, because oftentimes the output of a risk assessment is the safety integrity level required to bring to bear against a specific hazard scenario. So a SIL, or safety integrity level, it is the measure of the efficacy of a safety instrumented system. And it's really used in two different senses. It's one sense that it's used is in a sense of specification, or the SIL target. And the other sense that it is used in is in the sense of performance, or the SIL achieved. An example I like to use is if I'm the mayor of my town and I decide that we need to have a new bridge in town, I will have my city planners draw up what the specification is for the bridge. So the specification might be that it has to hold 10 large trucks. But then we'll go to a structural engineering firm and have them design this bridge, and they would at a minimum hit the specification, but they might exceed it, and they might design a bridge that'll hold 12 large trucks. So safety integrity level is used in the same sense. There's a sense of a SIL target, which is what you get out of a risk assessment. And then there's a SIL achieved, which you get when you've designed your SIS. So when you are coming up with what your SIL target is, it's basically a function of how much additional risk reduction you need. So this table is taken right out of the 61511 standard, and you can see on the rightmost column there is the target risk reduction, and they give you a range. And then over on the far left column, you see the SIL level that applies to it. So basically, there's a map between SIL level and risk reduction. The column in the middle is the probability of failure on demand, and in the PFD, or PFD average, is just the reciprocal of the risk reduction factor. So let's jump into the meat of this webinar, and which is going over the various risk assessment methodologies. And we have several of them here to go over. And we're going to go over each of them, and we're going to briefly talk about the details of them and what some of the trade-offs are. Now, the first thing I want to point out is that different risk assessment methodologies are either quantitative or semi-quantitative or purely qualitative. And this leads directly into what their trade-offs are. With each of the methodologies, I'm going to be showing this graph repeatedly. It's going to be the same graph. But the graph shows 3 dimensions of information. The green bar is the study, the cost of the study, the cost of the risk assessment study itself. And these are just relative scales. This is all qualitative information here, but I'm just trying to show the trending. So that's what the green one is. The red one is if you decide that you're going to control your risk in your plant based on the output of a given risk assessment study, there are going to be some trade-offs in terms of operational cost and capital cost to install and maintain those protective systems. So that's what the red bar is. And then the black bar is just a representation of the quality of the study. So a tall black bar is a study with good quality, and a short black bar is a study with not such great quality. And these are all, again, these are just all relative scales. So the first methodology we're going to look at is risk graph. So this is a kind of a generic picture of a risk graph, and the way that this works is you enter into the graph over here on the left, and you kind of filter down on these different categories until you get to one of the W columns. And so the categories are kind of listed here. You know, you have a consequence category, and you have different types of consequences within that category: minor injury, several deaths, etc. And then the next tier would be the F tier, where you have frequency and exposure. And then you go down to the P tier, possibility of avoidance. And then you select, you end up binning your final decision based on the W, the spectrum of W's that you're in, which is probability of occurrence in this example. And then from those W columns, you just pick out what your safety integrity level is, if it's a number. Or if it's an A, what it's telling you in this example is that you would want to add some additional risk reduction, but it doesn't need to be an SIS. Or if you land on the B, it means that a safety instrument system will not be sufficient in controlling your risk so that you meet your corporate risk tolerance criteria. So one of the great things about risk graph is that it can be very fast. You can do many scenarios very quickly. So the cost of your study is not going to be very much of a factor. One of the weaknesses is that if you look at these definitions, if you look at the difference between several deaths and many deaths, well, the way that these definitions here are written in this example is actually very poorly written. What you want out of your definitions when you use a risk graph are very concise definitions so that there's no ambiguity and so that you can control consistency. You know, if you have a risk assessment study team gets together and they do an assessment on one of your process trains, and then the following month you have a different team do an assessment on the sister train, you really want to get the same results, and that's going to be strongly dependent on how well these definitions are written out. So that's one of the weaknesses of a risk graph. Another item is the calibration. This is just an example here. This example is taken right out of the standard, the IEC 61511-3 standard, and you know it's just an example. But you have to calibrate these things. You don't just pull out the information from the standard and say this is how we're going to do it for my site. So what you do when you calibrate them, you pick out a couple of scenarios and you compare them. You compare the results of your risk graph with the results from more capable risk assessment techniques, which we're going to talk about here. So that's one of the other features of risk graph. They really need to be calibrated. And this particular one, you can see it really has 4 tiers. There's 4 different categories. You can have as many or as few categories as is required for controlling risk at your site. And again, that all comes out in the calibration. So when it comes to risk graph, again, the cost is quite low. You're going to have some additional cost over some of the better techniques in capital cost and operational costs, and the quality is kind of mid-range. In my opinion, a risk graph is actually a pretty good technique because you know you can calibrate it and you can control the variables. You just got to be diligent in doing that. Now, the next category of risk assessment technique we're going to discuss is layer of protection analysis. And there are several different flavors of it. And what I want to first do is go over some of the basics of LoPA. So first thing I want to do is talk about the mathematics of risk assessment. And this is applicable to LoPA, to quantitative risk assessment or probabilistic risk assessment, and also to the bow tie that we're going to be talking about later in this presentation. So let's say that I have 3 balloons tied to my mailbox because I'm having a garage sale and I want people to identify where I'm at. And I get to wondering, because I'm kind of nerdy, well, what is the frequency of all 3 balloons failing? What is that frequency? And let's assume that for each individual balloon, we know the frequency of failure of a given balloon, and we also know the probability of failure of a given balloon. And it's not necessarily the same for the red, yellow, and blue balloons, or they could be different. And so the frequency of all balloons popping is simply the frequency of the red balloon failing times the probability that the yellow balloon has already failed, times the probability that the blue balloon has already failed, plus the frequency of the yellow balloon failing times the probability that the red balloon has failed, times the probability that the blue balloon has failed, plus frequency of the blue balloon failing times the probability that the red and yellow balloons have already failed. That's the frequency of all 3 balloons failing. Now, what if I further ask the question, what is the frequency of all the balloons failing, but I only care about the case when the red balloon is the last one to pop? Well, that's just the first term, the frequency of the red balloon failing times the probabilities that the yellow and blue balloons have already failed. So this is just a kind of a simplified take on what is the mathematics employed in risk assessment. It's this combination of frequencies and probabilities. So let's go back to this risk matrix for a second and take a look at what we call the tolerable frequency of occurrence. For a given hazard scenario, remember, one of the things that you get from your PHA is you rank what the consequence severity of that hazard scenario is. Well, a lot of times the way that we determine what we need for additional risk reduction is we go to that consequence severity, say a single fatality for a given hazard scenario, and based on what it says in our corporate risk tolerance criteria in the risk matrix, we just map to where the tolerable frequency of occurrence is, just as I'm showing here. So this here says 10 to the negative 4th events per year, which is a frequency not greater than 1 event per 10,000 years. So a lot of times this is how we are actually making this calculation in terms of how much additional risk reduction we need. In this case, it would be 4 orders of magnitude of risk reduction. So if I look at LoPA from 50,000 feet, what I'm really doing is I'm taking the frequency of the cause of the hazard, whatever's causing that hazard scenario to occur, and I'm multiplying it by some other dimensionless factors, which we're going to go into. And then I take all of that and I divide it by the tolerable frequency of occurrence. And you can see here that I'm dividing a frequency by a frequency, and it gives me a dimensionless value. And if that dimensionless value is greater than 1, it is equal to the additional risk reduction I need in that hazard scenario to bring the scenario within the envelope of the corporate risk tolerance criteria. Or if that ratio is equal to or greater than or less than 1, then I don't need any additional risk reduction. I'm already meeting my corporate risk tolerance criteria. Now I want to talk about next what I call LoPA elements. And here are the LoPA elements. So just from left to right, there is an initiating event. You'll notice that there's only one initiating event. And the next there are enabling conditions, and there may be several enabling conditions. Similarly, there may be several conditional modifiers, and there may be several independent protection layers. And you multiply all these together and you get what I call a mitigated scenario frequency. You may have seen literature that calls this parameter the mitigated event likelihood. For a number of reasons, I don't like using that term, so I'm going to call it the mitigated scenario frequency. But it's just the frequency of the whole scenario playing out after you've considered the impact of the initiating event frequency, the enabling conditions, conditional modifiers, and independent protection layers. Now, this structure here is what I call a cause-consequence scenario. And again, notice there's exactly one cause. And just kind of to drive the point home from a couple slides ago, you have one of the elements, the initiating event, has a dimension of frequency, and all of the other, well, the enabling condition, conditional modifiers, and independent protection layers are all dimensionless, and you multiply them together and you get this frequency, mitigated scenario frequency. And just to recap, what you do with that mitigated scenario frequency is you divide it by the tolerable frequency of occurrence, and if it is greater than 1, it's equal to the additional risk reduction that you need to control your risk. And if it's greater than, or rather if it's less than or equal to 1, then you don't need any additional risk reduction. And when it comes to risk reduction, these are your risk reduction targets. That's just a reciprocal of the probability of failure on demand that you would need. So for example, let's say that I do my math on a hazard scenario and it says I need to bring one order of magnitude of risk reduction to the scenario, so a risk reduction factor of 10. Well, if I take the reciprocal of that, that is the probability of failure on demand that the maximum probability of failure on demand that I would need to have over any protective element. We're going to go over this more here in a little bit. So let's talk directly now about initiating events. So an initiating event, or the cause, or the initiating cause, it's the change in the plant which causes the hazard to develop. So if there is a failure or an error made that causes the hazard in the scenario to develop. Now, as we have already mentioned, there must be exactly one initiating event per cause-consequence scenario. The initiating event must be the last thing to occur, and I'm going to talk more about that in a second. And I want to harken back to the balloons that we talked about as to why I would be interested in the case where the red balloon is the last failure to occur. This is what we're doing in a LoPA or even in QRA. Now, going forward in this presentation, just for to save on real estate on my slide set here, I'm going to abbreviate the term cause-consequence scenario with just the term CC scenario. Examples of initiating events would be a instrument failure, control instrument failure. It can be a mechanical failure, such as a seal failure in a pump, for example. It can be an operator error, or it can be a loss of utility, loss of electricity, or loss of instrument air supply. All these can be initiating events for a hazard scenario. So let's take a look at this simplified diagram here where I have a pressure control loop consisting of a pressure transmitter, a DCS, and a pressure control valve. And then also on this pressure vessel, I have a pressure safety valve or a pressure relief valve. And then let's talk about the sequence of failure. This is going to seem trivial to a lot of people, but it's fairly important. So if the pressure controller fails before the pressure relief valve fails, then the tank doesn't overpressure, because your pressure relief valve is going to work. It's going to relieve any pressure that is the result of a failed pressure control loop. However, if the PRV is the first thing to fail, let's say it corrodes up and it gets to a state where it can't work, and then after that the pressure control loop fails, well, then you do have the overpressure excursion because the PRV is not going to work. It's failed. So this is why the initiating event must occur last. In this example, the initiating event would be the failure of the pressure control loop. And it's also why each cause-consequence scenario must have exactly one initiating event. Next LoPA element we're going to talk about is enabling conditions. So enabling condition is a condition of the plant which must exist at the time of the initiating event in order for the hazard to develop. Usually this is the percentage of time that a plant is operating in a specific configuration or a specific mode. There can be several enabling conditions per cause-consequence scenario. And again, it must exist at the time of the initiating event. Examples of enabling conditions can be if you have a dryer, you're operating a dryer in your plant and you go into regen mode, right? So that could be an enabling condition, or it could be during a period of time of heightened risk, such as when you're loading a rail car. Conditional modifiers, another LoPA element. This is a condition of the plant which must exist for the cause-consequence scenario to develop to the full severity or the severity of interest. There can be several conditional modifiers per cause-consequence scenario, and it also must be independent from the initiating event. Examples of conditional modifiers can be occupancy and probability of ignition. So let me go back over some of that. So the enabling condition, it works on the hazard. Without the enabling condition, you don't get the hazard unless even when the initiating event occurs, because you need that enabling condition. Whereas the conditional modifier, it operates on the consequence. So let's say you have a scenario where you have a seal failure in a pump, and you have a vapor cloud envelop the area, and it finds an ignition source, and then you have a vapor cloud explosion, which results in a fatality. Let's say that's the hazard scenario that you're looking at. Well, if you don't have somebody there, like an operator, if they're not there in the area, then you still have a consequence. It's just a consequence of a different severity, and in that case, you might take credit for occupancy. Likewise, let's say that you didn't have an ignition source. You have the operator there, but you don't have an ignition source. So when the hazard scenario develops, you don't get a vapor cloud explosion. You get a vapor cloud, and the operator is going to suffer some negative impacts from being in the cloud, but it's not going to be the one that you're studying. It's not going to be the vapor cloud explosion. It's not going to be the consequence of interest. The next LoPA element we're going to talk about is the independent protection layers. So let's go back to the concept of a safeguard, which I briefly mentioned when we went over PHA. So a safeguard is really anything that will prevent or mitigate a consequence or its severity. So the bar is not very high for something to be qualified as a safeguard. So what we do when we do a LoPA is you take the list of safeguards from the PHA, and we'll see which ones of them can be elevated to the status of an IPL. And here are the criteria. It must be independent, reliable, effective, dependable, and it must be audited. We're going to go over each of these. I'll just note that there can be several IPLs, or independent protection layers, per cause-consequence scenario. So now let's talk about independence. What is independence? So the requirement is that IPLs, which stands for independent protection layers, they must be independent of the other LoPA elements in the cause-consequence scenario. And the reason is because the math which underpins the technique, layer protection analysis, because the math used can't account for dependencies, everything is required to be independent. Now, if you take a look at this Venn diagram, we'll look at the definition of an intersection, and then we'll take a look at the independence aspect of it. So an intersection is defined as the conditional probability of event A happening, given that event B has already happened, times the probability of event B happening. And events A and B are defined as being independent if the probability of their intersection is equal to the product of their individual probabilities, as it is here, as you can see here. This term here over on the right side of this equal sign is just the product of the probabilities. If the intersection of the events is equal to that, then the two events are statistically independent. This is the math that LoPA uses. When we do a LoPA, we're just multiplying these LoPA elements together in that cause-consequence scenario. And so this is the reason why everything is required to be independent, is because the mathematics which underpin the LoPA technique does not have the sophistication to account for dependencies. We're going to talk a little bit about that more when we get to QRA. Now, when it comes to dependencies, there's different Poincaré sections, or different dimensions of dependencies. So there's a intrinsic dependency versus extrinsic dependencies. There are positively coupled dependencies versus negatively coupled dependencies. And the dependencies, if you do model them, they can be explicitly modeled or they can be implicitly modeled. So just briefly, an intrinsic dependency is a dependency that was intended by design. For example, if I have a motor-operated valve, I, by design, intended for the operation of that valve to be dependent on the availability of electricity to drive the motor. That was intended in the design. An extrinsic dependency is a dependency where the dependency was not intended in the design. For example, if I've got two redundantly voted pressure transmitters monitoring one of my processes, you can have polymerization. If it's a polymerizing service, you can have polymerization in each of the impulse line sets. This is not intended in the design, but yet it is a dependency that would be a dangerous failure of both pressure transmitters. Likewise, if you have a calibration procedure that was errant. There was an error in the actual procedure, but you calibrate all of a given class of instruments with the same procedure, that would be an extrinsic dependency. And then another example here is if you have the same instrument engineer writing the specification for, say, a pressure transmitter, if the instrument engineer is young and unexperienced, they might not know to choose the metallurgy for the diaphragm that would be resistant to hydrogen embrittlement. So these are all examples of extrinsic dependency. In terms of the coupling, a positively coupled dependency is simply where the probability of the second event happening increases if the first event happens. So if you have event A happen, it increases the probability that event B will also happen. That's a positively coupled dependency. Whereas in a negatively coupled dependency, if event A happens, it actually decreases the probability of event B happening. Positively coupled dependencies are the assumption. In fact, the IEC 61508-4 standard doesn't even recognize negatively coupled dependencies. And that, of course, that's the parent standard to SIS systems. Negatively coupled dependencies, they do exist, although in nature they're very rare. I only know of a couple of contrived examples of them. And then the last dimension of dependency we're going to talk about is the modeling of it. You can model them implicitly or you can model them explicitly. Usually, the modeling of explicit dependencies has to do with things you can really get your arms around, like loss of utility. For example, if you have an electric grid failure in the region of your plant, usually that kind of dependency would be modeled explicitly. Many dependencies, however, are modeled implicitly. So if you're familiar with the SIL verification calculations of safety instrumented systems, beta factor modeling is an example of an implicit modeling technique. So in summary, the math which underpins layer protection analysis cannot account for dependencies. This is why a lot of times LoPA is called simplified QRA. And it's also why everything's required to be independent. The main takeaway is that if you have positively coupled dependencies, your results from your LoPA will be non-conservative. You will not be controlling your risk in the way that you think you are. So that's independence. Let's talk about reliability. It must be reliable. So simply put, an IPL's reliability is simply its probability of failure on demand, which is the likelihood it will not protect the plant when you need it. One of the constraints that are commonly observed, this is not required, but one of the constraints that is commonly concerned is that you can only credit an IPL if it provides a full order of magnitude of risk reduction. I've seen this in literature. In my opinion, if I can only get 50% reliability out of something, I'll take it. But anyway, that's reliability. There's not a lot to be said here. And again, the risk reduction factor is simply the reciprocal of the mean probability of failure on demand. The next quality a safeguard must have in order to elevate it to the status of an IPL is it must be effective. And the best way for me to describe effectiveness is that if you have 8 IPLs being credited against a hazard scenario and any 7 of them utterly fail, and you only have one that's still working, that one is all you need. That's what effectiveness is. Now, there's a couple different ways that an IPL can be effective. It can either prevent the hazard from propagating into the consequence, or it can mitigate the consequence of severity. It's got to be effective, and also it's got to work before it's too late. So we're going to talk about this a little bit more. So let's first talk about the preventative type of an IPL. You can see that when the IPL works, it moves the frequency of the event of the consequence to a lower and lower frequency rate. So this is preventative application of an independent protection layer. However, independent protection layers can also be mitigative. So something like a deluge system or a dike around a storage tank. So if you talk about a dike and you have a loss of integrity of your storage tank and you lose its content, if you have a dike built around it, you still have a consequence. You just reduce the consequence severity, so you've mitigated it. So that's what you do when you're mitigating, when you use a mitigative IPL. Let's talk about time parameters. This is actually can be a very in-depth subject, but I'm just going to touch on it briefly. There's different kinds of time parameters. So there's a process safety time, there's an interlock response time, or IPL response time, if you will, and then there's what's called the maximum allowable response time. The process safety time in IEC 61508-4 is defined as starting when the initiating event occurs, so when the cause of the hazard scenario occurs. That's when the process safety time clock begins ticking, and it stops when there's no longer any effective action that you can take that will prevent the consequence. So the time elapsed between the initiating event and this point of no return is the process safety time, oftentimes denoted PST. Whereas the interlock, or IPL response time, it actually starts when the process variable being monitored achieves the alarm threshold that you set the interlock at. And the interlock response time, it stops when the final element of your interlock achieves a safe state. So let's say you're going to close a valve on high temperature to prevent against a thermal runaway in a reactor. Well, when the temperature gets to the alarm point, that's when the interlock response time begins, and the interlock response time stops when that valve actually achieves a safe state. The inlet valve on the reactants actually closes. Now, the maximum allowable response time is a parameter that I really like. It came out in the February 2014 publication by the Center for Chemical Process Safety, the Initiating Events, and IPL's the Blue Book. And it actually ties these top two together. So the maximum allowable response time, it starts when the process variable gets to the alarm threshold, and it stops when you can no longer take any effective action to prevent the consequence. And so it kind of ties both these ideas together. The next quality a safeguard must have in order to be promoted to an IPL is it must be dependable. So dependability is validated by monitoring the performance of an IPL during the life of the plant. So if you're going to be taking credit, for example, for pressure relief devices, you need to keep a record of when they've worked and when they have not worked, when you can prove that they should have worked but they didn't for whatever reason. And you keep a database of the performance of your IPLs, and then periodically you should go back and update your risk assessment to make sure that they're consistent with your actual measured value. This activity in the process industry is one of the weakest points. This feedback loop is one of the strongest aspects of the safety life cycle, the 61511 safety life cycle, and it's one of the weakest parts in our industry because of the tools and techniques, guidelines, and training really haven't been developed along these lines fully yet. This is also the subject of the third webinar in our series, so stay tuned in February. The last quality of a safeguard in order to elevate it to the status of an IPL is it must be audited, which is tested. So you got to test these things periodically. You got to prove that they're still working. You want to detect any failures, and then you want to also collect the data that you need to provide that feedback loop that we just spoke about. A lot of times an IPL is the test interval for an IPL is just set by what we call a REGAGAP, a regular and generally accepted good engineering practice. So if you have that high temperature closes a valve, and if it's not an SIS, if it's just a regular BPCS IPL, then you might say that, well, a one-year test interval would be REGAGAP. That would be pretty good. So that's how those are set. The test intervals for safety instrumented systems are actually determined, are proven by calculation. So you have you've got more flexibilities, but you also have more constraints. Certain of your IPLs can be very difficult to actually test, like check valves and level switches. They can present difficulties in making practical tests. In the case of check valves, a lot of times what's done is they're just replaced at a certain interval. And then IPLs which include an operator response required, the operator portion of that IPL, it would be the requirement to have the operator periodically review the SOP directing them what to do when that alarm occurs. And that brings us to the mitigated scenario frequency. So this is just a product of all of your LoPA elements. It's the frequency of the consequence that you can expect after you've taken account of the enabling conditions, conditional modifiers, and independent protection layers. The mitigated scenario frequency also is equal to the rate of challenge of any safety system that you subsequently put on to on your system to protect against the hazard scenario, if it'll allow a greater excursion. What I mean by that is that if you have a high pressure scenario and you decide that you need additional risk reduction, so you're going to put in a some sort of pressure interlock, the mitigated scenario frequency is the frequency with which that new interlock will be challenged, assuming that the initiating threshold for that new interlock will allow a greater pressure than what the other protective devices are already allowing. So with that lengthy preamble on LoPA, let's take a look at the various flavors of layer protection analysis. So the first one we're going to talk about is the worst case scenario. So the worst case scenario is if you have several different causes for the same consequence or the same hazard and consequence. What the worst case method has you do is you take into account only the cause that is the most frequent, and you design to protect against that. This only really works if that worst case that you select is orders of magnitude at a higher frequency than the other causes, and if the IPLs that you choose to protect yourself from them also apply to the others. So the example is to say there's several causes for an explosion, but you only manage the risk of the most frequent cause. So you can see where that can leave some gaps in your armor. You might not be controlling risk the way that you want. So this is not really the case that I'm very familiar with, because I've never seen it actually used practically. And you can see where I've mapped it here. It's got a fairly low effort. The cost and operational costs are not great, but then the quality of it is also not great, which means you can be exposed to greater risk than what you think. The next one is what we call single cause. So in the single cause is when again, it's the same setup. If you have several different causes for the same hazard and consequence, here you're treating you're controlling risk for each one of the scenarios, the cause consequence scenarios from each of the causes. However, you're doing so myopically. You're treating each one of them as though the others didn't exist. So the example is, if you assume there are several causes for an explosion and you manage them so that the hazard for each of them occurs less than or at the tolerable frequency of occurrence. So if your tolerable frequency of occurrence is, say, once every 10,000 years for a single fatality, for example, and if you have two separate causes for the same hazard and consequence, and for both of those you achieve that once every 10,000 years, well, if you consider them both together, then the actual consequence that you're looking at will occur at once every 5,000 years. You'll be exposed to a greater amount of risk than what you want to be, and so that's the pardon the pun, that's the hazard of myopically looking at each cause one at a time. And you can see the cost is a little greater because you're evaluating all of the hazard scenarios, not just the worst case as you did in the prior example. Your implementation and operational cost is a little bit greater too, because you're going to be installing more protective devices and you get a little bit better quality. The last one we're going to talk about is cumulative LoPA. So in cumulative LoPA is where you have those several causes for the same hazard and consequence, but what you do is you consider them all together. So that's really the best way to go is to consider everything together. And we're going to look at how this works. So this is my burner example. So this is burner light. There's not a lot here, but it makes the point. So let's say that there's two separate cause consequence scenarios. Both of them will lead to the same consequence scenario of a deflagration in your firebox for a fired process. So the first scenario is caused by a momentary drop in fuel pressure. So the fuel pressure falls off, and then you lose combustion, and then the fuel pressure is reestablished, and now you're filling your firebox full of uncombusted hydrocarbons. The second scenario is where you have a loss of combustion airflow. So let's say your forced draft fan fails, and your mixture gets too rich to burn, and then likewise you have a loss of combustion. Both of these scenarios set you up for deflagration. So if the same safeguard, in this example, a safety instrumented function, which closes the fuel safety shutoff valve on loss of proof of combustion, if you can qualify that as an IPL, then the math is pretty straightforward. The risk reduction factor of the target of the additional risk reduction that you may need, or the CIF, is simply, you just simply add the mitigated scenario frequencies from both scenarios together and then divide that sum end by the tolerable frequency of occurrence. Now, a caveat is that if the same CIF is not used to protect every cause consequence hazard, then the math is a little bit different. It's doable, but it's beyond the scope of this presentation to go down there. The reason it's more expensive on the study is because you're considering everything in the same consequence scenario. All those separate causes are going to be considered together, and they will cause you to design more robust protective functions. However, doing that, you will control your risk to a much greater degree. And this is really a preferred method, just analogous to the way hazard and operability analysis kind of is considered the sweet spot in process safety for the amount of effort you put in versus the quality of information you get out. Cumulative LoPA holds that for risk assessment. That's really what in my opinion anyhow, the safe spot, and what we see probably the most of. The next risk assessment methodology we're going to talk about is event tree analysis. Event tree analysis is quite similar to LoPA. In fact, it's almost identical. It's the same kind of idea. You have a single frequency, a single initiating event frequency, and then you have other elements. Here I have them listed as enabling condition, an IPL, and conditional modifier, but they can be several IPLs, etc. The difference is that at each one of these splits, you have the complement activity. So here at this split, for example, you have the independent protection layer failing. This is where it fails, probably a failure on demand. Where up here, this is the complement of it. This is where it works. And so the nice thing about an event tree is that you get a full spectrum of all the possible outcomes for the cause consequence scenario. However, the event tree only really lends itself to doing the single cause type of evaluation. And I have seen where event tree is actually called a LoPA diagram. So it's very similar. I kind of scored it in a similar way to the single cause LoPA, because it essentially is the same thing. You get a little bit better quality of information out because, like I said, you look at every possibility. Next, we're going to talk about quantitative risk assessment, sometimes called probabilistic risk assessment. QRA, or quantitative risk assessment, it's really the same kind of evaluation as cumulative LoPA, except we use a different tool, and the tool we use is equipped to handle dependencies. One of the features of QRA is because you can handle dependencies, a lot of times those dependencies are allowed to exist between what you already have in your system and the additional risk reduction that you're planning to put into your system. For example, let's say you have a scenario hazard, you're going to need to have a safety instrumented system. Now, most of the time, safety instrumented systems are independent of everything else. In fact, in clause 11 of the SIS standard, it says that. It says, they really should be independent, but it's not an absolute requirement. There's some wiggle room. So you can put in a safety instrumented system where, say, you're using the same transmitter as one of the other protective functions or even the initiating event in the scenario. So this is the power of QRA, is the ability to model for dependencies. Any type of dependency can be modeled. There are several different varieties of dependencies. There's series parallel dependencies. There's dependencies between frequency elements and probabilistic elements, etc. There's several different kinds of dependencies, and when you execute QRA, it's really an exercise of going through the modeling of those various dependencies. So QRA represents a very sharp pencil. The big downside is that the engineering man hours that you need to put into the study is considerably more than the other techniques that we've discussed so far. It's an expensive route to take, which is why it's not really sitting on top of the heap. The one that's probably the most recognized is cumulative LoPA, and this is the reason why, is that the QRA is just so much more expensive. But because of that, you're going to be able to take credit for all of the protective functions in your plant. When you're in a LoPA and you're going through a hazard scenario and someone says, well, we have a high level that controls a valve, and then somebody else says, hey, we also have a high level alarm from the same level transmitter, Well, the unit managers will say you can't take credit for the alarm because it's not independent. It uses the same transmitter. That's if you're doing a LoPA. But the unit manager will be sitting there and say, hey, wait a minute, how come I can't use that alarm? It works. I calibrate it, I install it, I make sure I know it's going to work. And we have this this constraint of independence that we keep pointing to, saying, well, because it's not independent. So and it comes down to the tool we selected can't model the dependency. So this is where QRA shines. You can model the dependency. However, a lot of times the cost of executing the QRA will outweigh the benefit of just buying another, or rather not buying another level transmitter. So that's where QRA falls at. In some cases where that additional risk reduction is very expensive. So let's say you have a 30-inch Coriolis meter or a gas chromatograph analyzer that you have to pay for your additional risk reduction, and you might be able to avoid that additional cost. That's the appropriate time to do a QRA. Next thing we're talking about is a bow tie analysis. Now, I'll tell you, there's two different things that are called bow tie. One of them is just a presentation of information. That's not what I'm talking about. This one is actually called bow tie analysis. And it's really the same thing as a QRA. It's done in a fault tree like a QRA. And the only real difference is that at the top event of the QRA, you have the conditional modifiers, which lay out the probabilities of the different possible consequences. So remember, we were talking about the probability of an occupancy of the operator versus the operator not being there. We're talking about the probability of ignition versus no ignition source. These would be splayed out here across the top gate from the bow tie. And that's the main advantage of it. Other than that, it's very much the same as the QRA. That gives a little bit more cost to execute, but it represents really the sharpest pencil we have when it comes to risk assessment. Now, I'll just point out that the capabilities and application of quantitative risk assessment or probabilistic risk assessment and bow tie analysis, it is a topic of our second webinar that will be announced for January. The last methodologies we're going to talk about are what we call the matrix methods. And so the three most popular titles they go by are implicit LoPA, safety layer matrix, and three-dimensional risk matrix. So implicit LoPA is pretty straightforward. For your consequence severity that, again, you get from your PHA, you look at what category you fall into, and then you look at the event frequency. Now, in application, this event frequency is skewed by other protective elements that you're taking credit for, other existing safeguards. And so you kind of pick which column you fit into here, and you just cross-reference it to the performance of the additional risk reduction that you might need. So if you end up down here in NA, then you're good. You don't need to do anything. In the purple non-SIL, this might be a BPCS IPL. Then you have for blue, green, and orange a SIL 1, SIL 2, and SIL 3 safety instrumented function. And if you end up here in the red, then what's being said is that you need to look at redesigning your plant to do something perhaps inherently safer design. So that's implicit LoPA. For safety layer matrix, it's quite similar. You take a look at your consequence severity in terms, in this example, of minor, serious, or extensive, and then you have the initiator frequency comes in at high, medium, and low. You count out how many safeguards you already have for that scenario, and then you cross-reference to the additional risk reduction that you're looking for. It's very similar to implicit LoPA. And then finally, we have three-dimensional risk matrix. And again, this is very similar. It's just a different presentation, really. You have the initiator frequency, the consequence severity, and the effectiveness of the other safeguards, and you sort of stack them together here like this. So with all three of these matrix methods, the implicit LoPA, safety layer matrix, and three-dimensional risk matrix, proceed with caution. The application of these methods usually include a significant amount of subjectivity when you credit safeguards, which makes it very difficult to control consistency at your site and even within the same study. If you put enough work and diligence into controlling those variables, these can be good methods, very much like the risk graph. However, I have personally seen major problems with cost overruns. In one particular project, we were brought in to do one of the downstream functions with the safety instrumented systems, and we noticed that A, everything was SIL 3, and B, none of the existing features of the plant design were given any credit for risk reduction. I'm not saying these are bad methods, but they really need a lot of bolstering before they become good methods. And so I scored them accordingly. You know, low quality, low cost, or they can be quick and dirty. So and they can result in high operational and capital costs, which was what my experience was. So that ends our survey of the different risk assessment methodologies, and I guess we can take any questions. Please type any questions into the Q&A box.
All right, so we do have some questions here. The first one, it asks the questions in the risk graph slide, aren't W1 and through W3 reversed so that the relatively high probability W3 high consequence risks are SIS not sufficient? So they are reversed. My slide has an error on it, and they should be ordered. The labels on them, W1, 2, and 3, they should be juxtaposed, so it says W3, W2, W1. So good eye, whoever submitted that question. That is correct. They are reversed. Next question comes from Sarah, and she's asking, what's the difference between frequency and probability, as many use these interchangeably? This is a great question. Probability is used in terms of challenges. When you ask about the probabilities, let's say you roll a dice, a 6-sided dice, and you say, well, what's the probability of me rolling a 1? Well, you should roll a 1 time in 6 challenges on average. So the base dimension there is the number of challenges. So when we talk about a risk reduction factor, let's say we have a protective function that has a risk reduction factor achieved of 100. So then we take the probability of failure is 0.01. What this says is that this protective function is not going to fail more frequently than 1 time, or more often, I should say, not going to fail more often than 1 time in 100 challenges. So that's probability. For frequency, the frequency has a time base, so it's just, you know, events per hour or events per year. So the dimensional unit for probability and frequency are different. A lot of times it's not too difficult to convert frequency to probability and probability to frequency, but it's not a straight 1-for-1, and it might be a good thing to add when we go through our second webinar in January to kind of look into that a little bit closer. So thank you for that question, Sarah. Next question comes from Dave. The question is the LoPA equation wrong if we don't explicitly consider the order of failures? The literal answer is yes, but in practicality, it's kind of a self-correcting issue. You know, I've never seen a risk assessment team go through a LoPA and fail to understand the importance of only qualifying a hazard scenario as propagating into the consequence of interest when all the protective functions don't work. I mean, it's kind of cooked in there. So I don't. So yeah, you have to consider order of failure at all times, but it's usually where people naturally land at during the meeting. Next question comes from Anonymous. The question is, can the initiating event be termed as the cause in the cause-consequence scenario? So yes, initiating event is synonymous with cause. So those really mean the same thing. So yeah, absolutely. Next question comes from Nathan, and Nathan asks, whether LoPA deals with multiple cause or consequence pairs, how accurate is LoPA? So LoPA, you know, if you have a hazard consequence, if you have a hazard that can propagate into a consequence, and if there is only one cause for that hazard to manifest, then any version of LoPA is pretty accurate with one caveat, which I'll get to in a second. However, if you have a hazard that can propagate into a consequence which has multiple causes, in other words, there's multiple things that can cause the hazard to manifest, then you really need to use a cumulative LoPA to be accurate with the same caveat. Now that caveat is there's actually two caveats. The one I was thinking about first is those other protective functions that are actually in your plant, and they very likely will work. However, if those other protective functions are not independent of other LoPA elements, then LoPA can't take credit for them. So let me explain further. Let's say that you have a pressure control loop, which is your cause. It's the cause of your hazard. The pressure control loop fails either at the controller, at the valve, or at the transmitter. And then you have also a pressure alarm off of that same pressure transmitter. Well, in that case, you cannot take credit for the pressure alarm in the LoPA because it's not independent of the initiating event. So, but there are times when the transmitter is not what has failed. There are times when it's either the controller, or it's the valve is the cause of the failure, which is the initiating event. And in those cases, the alarm from the transmitter very likely will work. Depends on how it's wired when it comes to the controller. So in terms of accuracy with LoPA, in that case, the LoPA will not take any credit for that alarm for that subset of causes for which the transmitter is not the problem, and so that derates the accuracy of the LoPA. So and this is where QRA comes in. Now that's the first caveat. Well, I guess I named a couple, and then the other one, which is not specific to LoPA, but it's specific to all these techniques, is you need high quality information going into your assessment in order to get high quality information coming out. So if you assume that your information going into the LoPA is perfect, and there's only one cause for the hazard, and there are no available protective functions which are dependent, then the LoPA, then any version of LoPA will be absolutely accurate. But you have to be careful with it. And then again, for the independence part of my answer there, we're going to look at that very closely in our January seminar or webinar. Next question, can LoPA be used for risk assessment where mitigation is not a SIS or a CIF? Yes, in fact, that's emphatically a yes. So one of the hats that I wear is the hat of an SIS design engineer. And I'm here to tell you that a safety instrumented system is the last thing you want to put in your plant. And the reason is that they're expensive. They're expensive for capital, and they are expensive during the operation. They're like the curse that keeps on cursing, because you've got to maintain them. You have to audit them to a higher degree. The paperwork's more expensive. They're just more expensive. And so it would be a fallacy to assume that if you're going to use a risk assessment, that it kind of automatically signs you up for going down the SIS path. Really, that's not where you want to go. You want to use other methods. You want to use less sophisticated methods of risk reduction. You want to use inherently safer design, those kind of things. So yes, you can use risk assessment where an SIS is just not in the picture, and that's really where everybody should be targeting. That's where you should be at. Next question, also from Anonymous. Should LoPA for SIS take mitigative IPLs into consideration to determine RRF? Yes, I believe so. You know, the examples that are listed here are gas detector, emergency response. I haven't really seen emergency response come into the picture in any meaningful ways. Usually by the time you get emergency response, your consequence, you know, the conflagration of your consequence is pretty mature. I don't, you know, you've already got the damage pretty much. But for gas detectors, absolutely. So for if you have a seal leak on a pump, for example, you go back to that example, and you have a combustible gas analyzer, and based on the alarm state of that combustible gas analyzer, you initiate your deluge to mitigate the consequence. Yes, you would use that for risk reduction. In that case, the risk reduction doesn't come from reducing the frequency of the consequence. It comes from reducing the severity of the consequence. Next question from Anonymous. How do you typically mitigate an RRF of less than 10, especially if you've taken all possible credit for BPCS IPL? And the second part of the question is, how can you tell the difference of that mitigation? How do you typically mitigate an RRF? I'm not sure I understand this question. Maybe my prior answer will shed some light on that. I don't really understand the question of how do you typically mitigate an RRF of less than 10. You know, IPLs that are instrument-based IPLs that have a risk reduction factor of target of not greater than 10, they are by definition a BPCS IPL, or a basic process control system IPL. They don't need to be controlled as a safety instrumented system. And that goes to whether or not they are preventative or mitigative. That goes for both categories. Next question, and so far the last question from Anonymous. I have noticed that HAZOP teams like to include failure of a safeguard or IPL as an initiating cause and risk rank it the same as a true initiating cause. This is obviously problematic in terms of LoPA. How do you typically handle that kind of scenario? So, yeah, I've seen that too, and in my opinion, and the way that our company operates is that a scenario which results in the loss of a safeguard is not a hazard scenario. Loss of a safeguard does not create a hazard. It creates a situation where you cannot detect or respond to the hazard with that safeguard. The way that this is handled when you get to the risk assessment, whether it's a LoPA or something else, is that we are already assigning a probability of failure of the safeguard. When we elevate the safeguard to the status of an IPL, we give it that reliability feature, if you recall from my presentation, and that reliability feature already has cooked into it the likelihood that it's not going to work. So that's how that is treated. So that is the last question that we have. I guess we'll give this a couple more minutes. And we are over our time here a little bit, so maybe we'll only give it one more minute. And I don't see any other questions coming in. So I'd like to thank everybody for hanging in there. Again, we will have another webinar on QRA and Bowtie in January. And then in February, we'll be presenting a webinar on really basic best practices for keeping your risk assessments evergreen. So thank you very much, and we'll talk to you next year.